In this video, we'll go over some descriptive statistics concepts that are useful for curve fitting applications. After studying this video, you should be able to understand the meaning of several common statistics concepts that we can use to describe a data set. Also, you should be able to use several built-in MATLAB functions to compute descriptive statistics. So, one area of statistics concerns measures of location. In other words, getting a sense for what the overall data is telling us. And you should be familiar with these concepts, one being the mean of the data or the average of the data. That's defined as the sum of all of the data values divided by the number of values. And there's a built-in MATLAB function to calculate the mean or average, and that's just the mean, where y now is a vector or matrix of data of values. Now, if it's a matrix, the mean function outputs a row vector that's actually the average of each column of the matrix. The median is the midpoint of a group of data, which may or may not line up with the mean depending on how the data is distributed. Median can be calculated using the median function in MATLAB. And the mode is the value that occurs most frequently in a group of data. And again, there's a mode function in MATLAB. So that's like if there was a set of data that was 4, 5, 4, 4, 3, 2, 4, 1, then the mode would be 4. Just in case you're not familiar with the concept of a mode. So we are interested in kind of the central tendency or the location of data. We also, once we know that, usually the average of the data is what we're most interested in. We would like to know how is that data spread about the average. And some measures of spread that are commonly used are the variance, where the variance is the sum of these residuals squared. And one note here, we call these the residuals, there's that term again, with respect to the mean, since it's the ith data point minus the mean. And then we square them, and the reason we square them is so that the negative and positive residuals don't cancel each other out. And then take the sum and divide by n minus 1. And in n minus 1, the 1 here is because we have 1 degree of freedom in the model that describes the data. And in this case, the model is just the mean, y bar. So that's just one value, so it has 1 degree of freedom, and that concept will become more important as we move into curve fitting. There's a built-in function to calculate the variance, VAR, and again, so that's the sum of the squares of the residuals with respect to the mean. You might see that looking somewhat familiar. Recall the idea of the Euclidean norm, and so that would be the Euclidean norm of the residuals vectors, where if we refer to E as the residual vector, and this is actually the square of the norms. Recall that Euclidean norm was the square root of the sum of the squares in a vector. So we would then take this value and square it. So there's another way to think about that denominator, or sorry, the numerator in the variance equation, and just to relate that back to some things we were talking about previously. The standard deviation is the square root of the variance, and the standard deviation is the most common measure of spread. And the reason that this is preferred over the variance is because here we're squaring the residuals which makes sense to do so that the positive and negative values don't cancel each other out, and then summing them, but now the order and the units on the residuals are not the same as the data itself. So taking the square root makes the standard deviation is now dimensionally consistent with the mean y bar. In other words, it has the same units as the mean. And MATLAB has the built-in function std to calculate the standard deviation. And again, like I said before, MATLAB statistics functions, you can input a matrix or a vector as the input argument for the data. If it is a matrix, the function operates column by column, and the output is a row vector. So as we're looking at a data set, one thing we might want to look at is how is that data distributed about the mean. And so a visual representation of that is called a histogram. And basically a histogram, what we do is count the data in what we call bins, where we will set up a bin, and in this case we'll say 16 values in that bin. Over here we've got in that central bin 212 values, and all that's coming from this output that I'll explain in a minute. So in statistics theory, if we have data that's normally distributed data, we would expect that if we took an infinite number of data points, eventually this histogram would have the look of the bell curve that you might be familiar with from previous coursework. MATLAB actually has a built-in function to generate normally distributed data, and that is this randn function. So that is generates normally distributed random data. So what I did in this little example here is just use that to add some uncertainty to a mean value of y bar equals 50, and then adding it basically 5 times that random number. Those are going to be between 0 and 1, or sorry, between -1 and 1. So adding those to that 50 creates this normally distributed data set. And then MATLAB has a built-in function histogram. HIST will actually produce the histogram, and the if you assign output, it will output the bin counts. The X output here are the centers of each bin, and the N output are how many of values in the data set are in that bin. So talk a little bit more about normally distributed data. So again, if we had an infinite number of data points, eventually this histogram would look like a nice smooth bell curve. And that bell curve is described by the Gaussian distribution function. F of x is equal to 1 over sigma times the square root of 2 pi times the exponential of -1/2 times x minus mu over sigma. So in this case, x is our data points. Mu is actually the mean, so it will be x bar, and sigma is the standard deviation. So that's the equation that describes the bell curve, and we're not going to go into proving this in this class, but I do want to talk briefly about this idea of a confidence interval. So what this bell curve says, and you can prove this, is notice this is in terms of standard deviations going away from the mean. Again, that's the mean, x bar, and what this tells us is that 34 plus 34 is 68. So 68%, we have a 68% probability, or we expect 68% of the data will fall in the mean plus or minus 1 standard deviation. And that's 68%. Now if we go out to 2 standard deviations, we add to that 68 another 27, And so we see 95% will fall in X bar plus or minus 2 standard deviations. And this will be a useful concept when we want to think about how well, as we get into curve fitting, how well does a model actually predict what we would expect to measure if we were taking additional data about a system. And we'll get into that in the next video as we start exploring curve fitting.